modeling like a class. But I think what I left is, why can't we just use this loss function, right? If we think about that, we have like a class like y to represent maybe y is like a binary class 0 and 1, and if this output y hat is like the weight here of maybe 0 and 1, but maybe this is like a continuous, but this one is discrete. We can use it to a certain point, but the thing is, if you think about the gap between the continuous value and the discrete value, it could be very high and hard to interpret. And that's kind of like the reason why people will then use a different loss function. And that loss function that we use for learning is called the, I'm not sure. It is like, I didn't provide a name here. It's like a cross, let me search. Yep, it's the cross entropy loss. But anyway, we'll go to that. Sorry, I didn't provide a name. Okay, so what we will use instead of that least square loss, because as we see that output of this sigmoid function is a value between 0 and 1, and then the reference that we use is like a strictly 0 or 1. Yeah, that's why we don't want to use that mean square error, but we can use it if you want to, but the performance will not be as good. And how about this binary okay, let me provide a name again. Cross entropy. Okay, so usually we will use what it called like a binary cross entropy loss, which is the loss function that is derived directly from the probability of, let's say, of that if we are given an input x and we are computing the likelihood that the model will provide us the class output as class y. So that is like the likelihood probability. And if we think about why we may be better using this loss function, let's see, right now we are considering the likelihood probability. If we look back at how we might want to interpret this value y hat here, we say it might look just like the probability of y being 0 or 1 given x. So it's kind of like, it looks very similar in a sense that we have the similar interpretation. If we were to use the sigmoid function here, and then we convert the linear mapping into like a score of a class, and then this score is actually like prop of y being 0 or being 1. But of course, that is also conditioned on our input x that is given right in the first place. So this is a probability. And if we look at the likelihood probability, that is this one, you can see there's some similarity there. And this likelihood probability came from the fact that, okay, if we say we want to find beta hat that are going to be the model parameters that is best fit for our given training data, right? We wanted to maximize the likelihood probability as much as possible. This is a probability of y given x, where y being the output and x being the input. But if I wrote x and y like this means that it's like the entire set of the y, that is the measurements, and the entire set of the x, that is like the input samples. Or on the other words, it's like probability of y1 up until ym given x1 up until xm. So that's like if there are 1,000 samples in the training, then when we solve for this argument max, we'll be solving using the likelihood between samples for, let's say, up to 1,000 samples. And I'm sorry, I just forget to write this beta here, which is like the model parameters that is associated with the mapping. So we can think of the likelihood probability as the probability that we might get from this, let's say, this pipeline, the pipeline here. We can think of that as this one. So this one as that one. Yeah. But the thing is, when we see this probability is like a joint probability between all samples, in machine learning, we usually assume that each samples in the training samples are uncorrelated or independently identically distributed, but usually just independency. So that means that we can write the joint distribution as the product of the distribution. Like that. And yes, I still forget the parameters, so we put parameters here. So that becomes this equation. But in here is like a joint of the probability. But the thing is, if you have probability multiplied with probabilities for, let's say, 1,000 times, the value becomes something very close to 0. So that's why normally people would take a logarithm onto this probability value so that they convert from the multiplication of value between 0 and 1 to the sum of the value between 0 and 1 to avoid what would happen from this multiplication that sometimes we call like an underflow problem. So when we take the log here, it becomes like a sum of log of probability, which is actually easier to compute with computer machine. Because if we think about the probability value, it's like a 0 and 1. When we take a log, it becomes like a digit with maybe a negative value. Let's say if the probability is like 0.5, then you have a value of negative 2. Sorry, yeah, negative 2. Something like that. So after we have this log of probability value, we can then start to think about what it means for, let's say, if we were given a sample X, and then we have this probability of being class Y, just like that. So actually, I shouldn't wrote it this way. This might sound really confusing. How should I do it? Okay, sorry. Actually, it may be better for me to write it this way. Maybe you can just ignore this for the time being and that as well. Okay, put this way. If I say that I have probability of Y given X, and including beta, and let's say if we have only 2 classes possible, then we have probability of Y equal to 1 given X beta, and probability of Y equal to 0 given X beta. Is that right? And it doesn't matter what this probability function could be, but the thing is, if your output could only provide like a 0 and 1, then that just means that you can either have this one or that one. So pretty much that means that if you're considering probability of y equal to 0, this is equal to probability of y, 1 minus probability of y equal to 1, beta. Okay, and then because of that, that means that this probability of y being yj, which is like being the value of y that was in our reference, which could either be a or b, you can think of this as you need like a choice to make when you know the value of y. So that's why sometimes people will convert this function into a function below. Like they may multiply probability of, actually this should be prob of y equal to 1 given x beta, and adding with 1 minus y, which is like a value 1 anyway, and multiply with log of 1 minus p of y equal to 1 given x beta. That's maybe a better way to write it. Actually, I'm sorry for writing this because I initially I thought that's a good way to identify, but it's actually not. Okay. Okay. And this value y will be the one that determine whether or not you want to use this probability or you want to use this probability. Let's say if your measurements has a value of, if the measurements at the j sample has a value of 1, that means you should use this probability to represent it, but not this one, right? If yj is equal to 1. And when yj is equal to 1, then this will be 0. So you will not use that probability. But if that yj is equal to 1, if that yj is equal to 0, then you should use this log of probability function, but not this one. So it's 0 or 1 here is like an indication of switching between the probability of y equal to 1 or probability of y equal to 0. So that is pretty much like the way that people put it. Okay, and the thing is, we know that probability of y equal to 1 or probability of y equal to 0 here, you can actually use like a sigmoid interpretation to represent it. So you can just put it down directly like that. And for this one, you just negate whatever previously this one was. That's it. That's like the loss function that we would use. Sometimes you can go further, as in if you can define that this log is definitely like a log in natural space, like log of natural value, log of E or ln, I'm not sure how you call it, like I'm not sure. Log of natural value, yeah. If you define this log as being like a natural base, then you can further decompose into the following terms. And okay, I will go back and do it slowly. Let's say if you further decompose them, this will be yj times x transpose j beta plus log of 1 plus exponential of j transpose beta. I believe this is going to be the first term. So you got this term. And then you will have another term which is like the rest of this function. But the thing is, if you look carefully at this one, okay, I'll just eliminate this one. if you decompose 1 minus exponential of something divided by 1 plus exponential of something, then that becomes 1 plus exponential something minus exponential something, and this will be 1 plus exponential something. Then you have 1 over 1 plus exponential. So this means that if you take the log over this term, then that means you will end up with a log of 1 minus log of 1 plus exponential term, and log of 1 is equal to 0. So that's why you will end up with only this term at the end. Yes. And after that, you may reshape it a little bit, such as maybe because we see that, well, in fact, we have these two things that are the same, we can maybe group them together. But to group them, that means that you kind of like grouping the samples that corresponding to the positive class, let's say, and grouping the samples that correspond to negative class. So that's why your summation will change. The notation for the set of the summation will change. Yeah. That's it, pretty much. So when you do the learning, you can simply use this as a loss function. This is only if you have, let's say, linear mapping, and then you fed them to the logistic regression function, right? As I mentioned before, like in this pipeline. But the thing is, how should I say? At this stage, we are learning logistic regression. This is the definition of our function. But when we want to extend this to something like neural network, and if at the end you still have like a logistic, that sigmoid function, and that is mapped to 0 and 1, pretty much that means that you can utilize that loss probably around this step. Maybe around this step to do your learning. It is like, because this is like representing the value after you pass through the linear layer and then the sigmoid layer. Yeah. But after that, this is like, it depends on how much the function, it's like how much we have applied the sigmoid function, how many times we have applied the sigmoid function over the linear mapping. So that's it. Okay. Actually, that's actually pretty much it for the logistic regression. It's pretty short, just like that, because the fundamental of that is kind of like, it depends on what we learn in the linear regression, and then now we add an activation function, let's say, then that's turned the problem into logistic regression, where this is like a binary classification, because we only get the output from the sigmoid function, where if the value of this output is close to 0, then that is like a probability of being, let's say, class 0, or maybe probability of being class 1. That's it. Yeah. What else? In fact, in this area, another thing that may be important is how you might want to interpret the result that you get when you, after you learn for the beta, that is like your model parameters that you get from the regression model. So this is like another thing that is important in this topic. Okay. First of all, the followings, I'm not sure if the stat model, the package that you can use for doing the logistic regression will still provide you this value, but I'm very sure that yes, of course they will give you like a p-value and a coefficient, but I'm not sure about the rest. So usually the value beta will have some kind of, I'm not sure if we can say it's a property. Okay, the value beta will have some kind of, it's like, okay, let's put it this way. If this is not a logistic regression, but a simple linear regression, the beta value will have some important meanings in mapping between x and y. If we just consider this term, like mapping from x to the regress value y, and if our x can only be positive, then that means that beta will represent some kind of relation, like a linear relationship between input and the output. But when this is turned into like the logistic regression problem, the difference between the two is like, how should we interpret this value into like a scale between 0 and 1, and that become like a chance of whether or not giving this input x, can we tell whether or not this input x should provide like a probability that class being class 1 or class 0. In this example, I kind of provide example where we have only one input features, that is the status of being students. Okay, maybe first of all, this is like a problem where we use logistic regression to classify whether or not the credit card will be defaulted. So defaulting credit card is like, it will be, the credit card will be canceled. So in this case, they use the student status as one of the input. And intercept here is like a bias value. Let's say if we have just one input, that means that if we fed this x into this linear mapping and then sigmoid function, our beta here could be just beta 1. But in this case, it's like beta 1, x1, because we have only one input. And the intercept is the term where correspond to like beta 0. Yeah, it's like DC component or maybe a bias value. So this intercept is this value. Intercept would be a value that give you like, it does not depend on x, it depends on like overall, are you likely to default this credit card, or are you likely to not default this credit card? So that is like the value for beta 0. And in this case, as you can see, regardless of whether or not that person is student, you have a negate 3.5 here, which we know that if we have a negate value, sigmoid function will map that to 0. So that means it is unlikely to default that credit card. So that credit card is unlikely to be canceled. But if our coefficient that correspond to the input x is like a positive value, it's kind of like dragging to the opposite direction. That means that if you are a student, then likely your credit card will be canceled. So if we plug everything into this mapping function, we can see that, okay, if x is non-student, then this value be 0. If x is student, this value be 1. And if you calculate them, then you can see that actually the probability of being cancelled given that x is student is higher. So that's how you interpret, or maybe let's say how the computer will calculate when you use it to provide the class of whether or not this credit card will be or will not be cancelled. And as I mentioned before, usually these two statistics will not be provided in the model because the standard error and set statistics. Actually, I think the standard error is the one that may not be provided. It is because the standard error with respect to the ground truth value of the coefficient beta. And usually we don't know that value. So usually we will be given this p-value and set statistic. We will see in detail what are they. Okay. Maybe first of all, p-value is representing how likely the null hypothesis will be rejected. What I'm trying to say is that the smaller p-value, the more likely the null hypothesis will be rejected. And in this case, and in most cases when you use statistical model, if they give you like a default p-value, some value, p-value usually means it's a p-value associated with the hypothesis where that variable is being 0. So it's a value of identifying whether or not the coefficient will likely to be 0 or non-zero. The smaller p-value means that the null hypothesis will be rejected. This means that the smaller the p-value, beta will unlikely to be 0. So beta will likely to be high value. So in this case, if we look at this table, intercept will unlikely, this is the value of coefficient beta. It's kind of correspond to that, for the fact that this is very unlikely to be 0. Yes, of course, the value is not 0 and it's actually negate 3.5. This value will a little closer to be 0, but it's still non-zero. It's 0.40449. That's the meaning of that p-value. And that statistic is like how far is this value from our hypothesis. That is, if we hypothesize that beta 0 is equal to 0, but in fact the actual value is equal to negate 3.5, that statistic will tell you how far is this value from the hypothesis of beta being 0. And how far in this case is like how far with respect to the variance of that value. I think, or maybe with this as well. I'm not sure, but I will check about that. Yeah. But it's more like the deviation from your hypothesis. In fact, it can tell whether or not, I think it's the variance of both. It's a variance of both, yes. It should be variance of both beta. And this is probably closer to the hypothesis than that one, if you think about. Everything okay? Actually, pretty much. Okay, this is just another example. Okay, so in previous example is the table on the left-hand side, where we see that if you're a student and if you see that coefficient is positive, it's kind of encouraged the chance that that credit card will be canceled. But in this case, when you add more features. It just turned out that there are other features that would kind of like outweigh that chance, such as the balance will have more impact towards making this credit card being canceled. And that's to the point that the students, the status of being students, is actually helping this it's actually helping this credit card from not being canceled. It's actually supporting the intercept that, oh, okay, generally I don't want any card to be canceled. I don't want it to be defaulted. Yeah. So pretty much that's it. And another thing that you can notice about is the p-value here for this beta income. That means in this example, it just means that income doesn't really have a lot of impact, and therefore it is possible that your coefficient could be close to 0. And in this case, it's actually closer to 0 than, it's actually the one that's closest to 0 compared to the rest. So that's what it means. And if we look at the statistic, yeah, the distance to null space, to the null hypothesis is closer. Yeah. So I think that's it. How to read the two table. You can go back and revise the information again, but I think that's all. Okay. Let's have like a 5 minutes break.